So we're going to find, I'll call it theta, the angle that the beam makes with the horizontal after we apply the 800 Newton load. And both of the springs have the same stiffness, 5 kilonewtons per meter. So the spring at A and the spring at B, both 5,000 newtons per meter. Okay, and then the 800, that's going to be reflected in our free body diagram for this. So the free body diagram will be pretty straightforward here. What do I want to isolate? What's the object I'm going to free from its supports and its connections? Right, this blue beam that goes from A to B. I have one applied force that's acting on it, that's 800 newtons. That's located 1 meter from A, and I'll just write it as 2 meters from B. What other forces act on my beam then, since I've freed it from its connections? Right, the spring at A and the spring at B. In the free body diagram, just like we've seen with springs before, it doesn't care it's a spring, it just cares that it's a force. So by convention, I assume that springs are in tension. I'll call this FA, and I'll call this FB. Clearly, they're not going to be in tension here. We can see that if this 800 newtons is down, there's no way that both of these can be down. But again, because of the Hooke's law version I use, where a positive deformation means it's expanding and negative means it's contracting, I'm going to stick with that and still assume that these are in tension and let the math tell me whether they're, one is in compression or they're both in compression. So here I have just the spring at A, the spring at B. I have two forces. I have two unknowns. So like I said, we don't have three unknowns in the free body diagram. So we might want to just take a second look and make sure that we're not missing one. In this case, we're not, because springs only exert a force along their length, or a linear spring only exerts a force along its length, and there's nothing else acting on the beam. So in this case, we really do only have two unknowns in the free body diagram step. And again, we can verify this, or at least double check this. All three of these equations still must be true. Well, we can take the moment around any point, but it still must be true that if we sum forces in the x at 0, sum in the y at 0, and the moment around any one point will be 0 as well. So if we start up here with equation 1, what is the sum of forces in the x direction equal to? What should my right-hand side be here? Right. If we look at the free body diagram, there are no forces in the x direction. I get 0 equals 0, which is true. It's just not helpful to solve for the unknown. But if we got 0 equals something that was not 0, then we would not be in equilibrium because we would have a net force in the x direction. So if you don't have three unknowns in your picture, one of your equations better be 0 equals 0. It doesn't matter which one, but one of them better be that so that it's still going to be true. Now if I look in the y direction, according to my free body diagram, I'll have a negative 800 minus FA minus FB. So two unknowns for my one equation, and now I can take the sum of moments. Which point should I take the sum of moments about? Right, A would be fine, or A is good because it eliminates FA. B would be good because it eliminates FB. So either one, I'll only be left with one unknown. I'd say here is the least efficient point because it'll have both an FA and an FB if I call this point C. So in this case, I'll just, for simplicity, do it around A. A or B would be equally good in this case. Taking the moment around A, I will have a moment caused by this 800 newtons. That's located 1 meter away from A. It's going in the clockwise direction, so it's negative. I'll have a moment caused by the force in the spring at B. That's located 3 away. Again, these equations are always written based on the picture I drew. So based on the picture, FB as drawn, is going to cause a clockwise rotation. So even though it is going to turn out that FB is negative, I don't want to put its value in here or presume that right away. I'm always basing all of these on the picture and then filling in values. Now if I look at my third equation, because I took the moment around A, I can solve FB. And FB, which we should expect, does turn out to be negative. That spring is in compression. FB turns out to be negative 267 newtons. So again, compression. Once I know FB, I can solve FA from equation 2. Will be a negative 533 newtons. So I know the forces in the springs. They're both in compression here. So they're both going to be shorter than they once were. Where can I go from here? Remember, what do I need to find? I wasn't asked to find the forces in the springs. I was asked to find what angle this beam is going to make once I apply this 800 Newton force on it. Right, we know K, so that will give us more equations I can write. So I could start there, or I know that I'm going to be able to get 2 equations out of that. But actually, before I write the equations down, how ultimately does that help us get to theta? What's going to happen when I press down on this beam? Well, both springs are going to shorten, but one is going to shorten more than the other. Right? Presumably, because they have the same spring constant, A is going to shorten more than B does because it has twice the force as B. So if I look at my picture of what's happening here, my beam is originally horizontal. I'm going to push down on it, so both springs do compress a certain amount. But A is going to compress more. So again, this beam is originally 3 meters long. I'm assuming a small angle of displacement, so I'm assuming that all of my displacement is going to be vertical in this case. So what happens is I push down, so it lowers, and then it's going to tilt because one side displaces more than the other. The right-hand side is going to displace by a distance of dB, or delta B. And then the left side is going to displace by delta A. So in this picture, what I'm interested in, though, is what's the angle of tilt since one side deforms more than the other side. That's the theta that ultimately I need to find. Yeah. So in this diagram, I'll come back to this in a minute because we know how to find delta A and we know how to find delta B because those deformations of the spring, those are related to Hooke's law. So I know that the force in the spring at A must be its spring constant times its deformation. Also, keep in mind this is going to be a geometric picture, so distances are always positive because what we're going to find in the end here, when we solve equation 4, negative 533 is equal to K, which is 5,000, times delta A. I do get delta A as a negative value because it is compressing. I get delta A as a negative 0.107 meters. In the way I drew this diagram, though, I'm ignoring the sign on delta A, delta B, because I know it's up here. It must get lower, and then it must shift downward there. So here, this delta A and this delta B, really it's the absolute values that I'm going to be using in subsequent steps. This is negative based on the assumption that positive is tension or expansion, negative is compression or contraction. So likewise in equation 5, negative 267 is 5,000 delta B. So spring B is going to contract by negative 0.0533 meters. Both are in compression. Both of the springs get smaller. That's why their delta values are negative in this case. Again, ultimately, what do I need to find? I need to find theta. How can I use this diagram to find the value of theta? Right, so here, if ultimately I need to find this theta, right, tangent I can use here. I know what the adjacent is to this angle is 3 meters. But what is the opposite to this angle? So I can write, right, the opposite is not delta A, it's the difference. It's only this distance here, which is, right, the difference between how much delta A contracted and how much delta B contracted. So this, delta A minus delta B, since we know this length is delta B, the whole length is delta A, so by the segment addition postulate from geometry, this must be delta A minus delta B. So if I want to use the tangent here, if I use opposite over adjacent, the opposite is delta A over delta B, and the adjacent is 3 meters. Again, be careful here. I'm going to just do, really it's the absolute values here because the geometry picture is different than what I got from the forces. So the difference is going to be really a positive 0.0533. Because that's going to be 0.107 minus 0.0533. So again, the opposite over the adjacent according to my geometry picture, this second picture down here. So I can solve my sixth equation by taking the arctangent to both sides. And I get, I put mine in degrees here, that theta is 1.03 degrees.